Good morning, all of you. In this session, I am going to explain about introduction about shafts and some simple examples on shaft problems. A shaft is a rotating machine element which is used to transmit power from one place to another. The power is delivered to the shaft by some tangential force, and the resultant torque or twisting moment set up within the shaft permits the power to be transferred to various machines like up to the shaft. In order to transfer the power from one shaft to another shaft, the various members such as pulleys, gears, and hubs are mounted on it. These members, along with the forces exerted upon them, causes the shaft to bending. In other words, we may say that a shaft is used for transmission of torque and bending moment. The various members are mounted on the shaft by means of keys or splines. What are the properties of shaft materials? Shaft material used for shafts should have the following properties. First one, shaft material should have high strength, and shaft material should have good machinability, should have low notch sensitivity factor, should have good heat treatment properties, it should have high wear resistant properties. So these are the example properties. Here for 40C8 material, 40% carbon material, ultimate tensile strength is 560 to 670 megapascal, and the yield strength is 320 megapascal. Okay, these are the corresponding properties. Okay. Where shafts are generally manufactured by hot rolling and finished to size by cold drawing or turning on grinding operations. The cold rolled shafts are stronger than the hot rolled shafts, but with higher residual stresses. The residual stresses may cause a distortion of the shaft when it is machined, especially when slots or keyways are cut. Shafts of larger diameter are usually forged and turned to size in a lathe. Types of shafts. The following two types of shafts are important from the subject point of view. Transmission shafts. So transmission shafts transmit the power between the source and the machines absorbing power. The counter shafts, line shafts, overhead shafts, and all factory shafts are transmission shafts. These are the examples for transmission shafts. Since these shafts carry machine parts such as pulleys, gears, hubs, therefore they are subjected to bending in addition to twisting. Machine shafts. These shafts form an integral part of the machine itself. The crankshaft is an example of a machine shaft. Standard sizes of transmission shafts: 25 mm to 60 mm with the 5 mm steps, 60 mm to 110 mm with 10 mm steps, 110 mm to 140 mm with the 15 mm steps, and 140 mm to 400 mm with the 20 mm steps. So these are the standard sizes of transmission shafts. The standard length of the shafts are 5 meters, 6 meters, and 7 meters. The following are the stresses induced in the shafts. Shear stress. Shear stress due to the transmission of torque, bending stress due to the forces acting upon the machine elements like gears, pulleys, okay, sprockets, okay, stresses due to combined torsional and bending loads. Okay, these are the important stresses induced in the shaft material. The shafts may be designed on the basis of strength and rigidity or stiffness. In designing shafts on the basis of strength, the following cases may be considered: shafts subjected to twisting moment or torque only. The shafts subjected to bending moment only. Shafts subjected to combined twisting and bending moment. And the fourth one is shafts subjected to axial loads in addition to the combined torsional and bending loads. Okay. In next class, we will discuss about these topics one by one. We shall now discuss the above cases in detail in the following pages. This is a solid shaft. Okay, this is the cross-sectional view of a solid shaft. D is the outer diameter of a solid shaft, and radius capital R equal to D by 2 is the outer radius of a solid shaft. Okay. Now this is the cross-sectional view of a hollow shaft. Okay. So small d is the inner diameter of the hollow shaft. Capital D is the outer diameter of a hollow shaft. Okay. Here K is the diameters ratio. Okay, K equal to inner diameter divided by outer diameter of the hollow shaft. Okay. This K value is very important for solving the hollow shaft problems. Okay. Now J is the polar moment of inertia. That means the moment of inertia about ZZ axis. Already we know that moment of inertia about ZZ axis equal to Ixx plus Iyy. From perpendicular axis theorem, the polar moment of inertia J equal to Ixx plus Iyy. Okay. For solid shafts, the polar moment of inertia for solid shaft J equal to pi d power 4 by 32. Okay. For hollow shafts, J equal to pi d power 4 by 32 into 1 minus K power 4. Here K equal to D by D, small d by capital D. Okay. From torsional equation, tau by R equal to T by J. Okay. From this equation, you can get the value of diameter of the shaft. Here T is the torque or twisting moment, tau is the shear stress, R is the radius of the shaft, and J is the polar moment of inertia. From this equation, the torque for solid shaft T equal to pi d cube by 60 into tau. Okay, so this is the derivation of torque transmitted by the solid shaft. Okay, so torque for solid shaft T equal to pi d cube by 16 into tau. Okay, so this formula is very important for solving the solid shaft problems. Okay, please note down this formula. In similar way, for hollow shafts, torque transmitted by the hollow shaft T equal to pi d cube by 16 into tau into 1 minus K power 4. Okay, so from the torsional equation tau by R equal to T by J, you have to substitute the value of R, tau, and J values. Okay, so the torque for hollow shaft T equal to pi d cube by 16 into tau into 1 minus K power 4. So this is the formula for hollow shaft. Okay, please note down this formula also. Okay, these two formulas are very important for design of solid and hollow shaft problems. These are the important formulas. Okay, these are important formulas for the solving the problems. Okay. So already we know that this is the formula for stress. Stress equal to load by cross-section area. Okay, so sigma is the symbol for stress, sigma equal to load by area. Here, the cross-sectional area for this solid shaft equal to pi by 4 d square, and for the hollow shaft, cross-sectional area A equal to pi by 4 outer diameter square minus inner diameter square. Okay, for tensile stress, sigma equal to P by A. For compressive stress, sigma equal to P by A. Here, P is the external load or axial load acting on the shaft. Here, sigma B is the bending stress. Sigma B equal to M by Z. M is the maximum bending moment. M is the maximum bending moment. Z is the section modulus. Okay. For solid shaft, sigma B equal to M by Z equal to 32 M by pi d cube. Okay. Here the Z for solid shaft, Z equal to pi d cube by 32. Okay. For solid shaft, Z equal to pi d cube by 32. For hollow shafts, Z equal to pi d cube by 32 into 1 minus k power 4. Okay, this is the formula for bending stress for hollow shaft. This is the formula for bending stress for solid shaft. Okay. In similar way, this is the formula for shear stress. Shear stress for solid shaft, shear stress for hollow shaft. Okay, here T equal to torque transmitted by the shaft. T equal to pi d cube by 16 into tau. From torsional equation, torque T equal to pi d cube by 16 into tau for solid shaft, and T equal to pi d cube by 16 tau into 1 minus k power 4 is for hollow shaft. Okay. Now capital E is the Young's modulus, small e or epsilon. Okay, sigma is the stress. Okay, Young's modulus is equal to stress by strain. So this is the formula for change in length. When a member is subjected to direct stresses in one plane, accompanied by a simple shear stress, this is the formula for maximum principal stress. Sigma T1 equals sigma 1 by 2 plus 1 by 2 square root of sigma 1 square plus 4 tau square. This is the formula for a minimum principal stress. Sigma T2 equal to sigma 1 by 2 minus 1 by 2 square root of sigma 1 square plus 4 tau square. So here sigma 1 is the stress induced in the component. Okay, that is axial or bending stresses. Tau is the shear stress. Okay, the maximum shear stress is tau max. Tau max equal to sigma T1 minus sigma T2. Okay, tau max equal to sigma T1 minus sigma T2 equal to 1 by 2 square root of sigma 1 square plus 4 tau square. Okay, this is a first type shafts subjected to twisting moment only. Okay, shafts subjected to twisting moment only. From this is the torsional equation, tau by r equal to T by J. Okay, from this equation, first of all, you have to consider torque or twisting moment, that is T. Okay, so this is the formula for solid shaft. This is the formula for hollow shaft. Okay, now from these two formulas, you can determine the suitable diameter of this shaft. Okay, for determine the solid shaft, you have to use this formula. For determine the size of hollow shaft, you have to use this formula. Okay, shafts subjected to twisting moment only. Here K equal to inner diameter of the hollow shaft divided by outer diameter of the hollow shaft. Now this is case number 2. Second case, shafts subjected to bending moment only. Already we know that from mechanics of solid subject or strength of metals subject, bending equation, simple bending equation, m by I equal to sigma by y equal to E by R. Already we know that from bending equation, m by I equal to sigma b by y. Okay, you have to calculate the suitable diameter of the shaft. Here m is the maximum bending moment, I is the moment of inertia, and sigma b is the bending stress induced in the shaft material, and y is the distance between centroid of the shaft and the outer surface. So already we know that bending stress for solid shaft, bending stress sigma b equal to m by I by y. I by y equal to z. Okay, z is the section modulus. Z equal to I by Y. Okay. Already we know that for a solid shaft, bending stress sigma B equal to 32 m by pi d cube. Z equal to pi d cube by 32 for solid shaft, and sigma B equal to 32 m by pi d cube into 1 minus k power 4 for hollow shaft. Okay. Now you have to use these two formulas for design of shafts on shafts subjected to bending moment only. Now shafts subjected to combined twisting moment and bending moment. This is a case, third case. In this case, shafts subjected to combined torque and bending moments. According to for solving these type of problems, you have to use maximum principal stress theory and maximum shear stress theory. Okay, you have to use these formulas for solving the shafts. Okay, if shafts subjected to combined twisting and bending moment, you have to use these two formulas. Okay, this is equivalent twisting moment TE equal to square root of m square by m square plus t square, and here this one is the equivalent twisting moment for hollow shaft, square root of m square plus t square. So this is according to maximum principle or normal stress theory. ME equal to equivalent bending moment. ME means equivalent bending moment equal to 1 by 2 into m plus square root of m square plus t square. Here m is the maximum bending moment. This is the formula for hollow shaft. Okay, for determining the size of the solid or hollow shafts, you have to use these two formulas for shafts subjected to combined twisting and bending moments. Now I am going to explain some simple example problems on design of shafts subjected to twisting moment only. So this is a question. A shaft is transmitting 100 kilowatts at 160 RPM. Find a suitable diameter of the shaft. Take maximum allowable shear stress as 70 megapascal. Okay, this is a given question for a solid shaft. Okay, and this one also a question for a hollow shaft. A hollow shaft is transmitting 100 kilowatts at 160 RPM. Find a suitable diameter of the shaft. Take maximum allowable shear stress as 70 megapascal and diameter ratio as 3:4. Okay. Here the question is same for a solid shaft and a hollow shaft. The main difference is for a hollow shaft you have to consider K value, that is the diameter ratio K equal to 3 by 4. Okay, you have to consider this value, diameter ratio for the hollow shafts. Okay. Now, first of all, you have to identify the given values. Okay, for this solid shaft problem, first you have to identify the given values. Here, n is the speed of the solid shaft, n equal to 160 RPM, and the power here tau is the maximum shear stress induced in the shaft material, tau equal to 70 megapascal. 1 megapascal equal to 1 Newton per mm square. Okay, 1 megapascal equal to 1 Newton per mm square, or 1 megapascal equal to 10 power 6 Newton per meter square. Okay, you can use any one. Okay, from given data, this solid shaft is transmitting 100 kilowatts. So this is the power transmitted by the solid shaft. Okay, power P means power transmitted by the shaft, P equal to 100 kilowatts. 1 kilo equal to 1000 watts. So 1 lakh watts, 1 watt equal to Newton meter per second or joule per second. Okay, so power is in meters. Now already we know that power transmitted by this shaft, power P equal to torque into angular velocity. Okay, this is the formula for solid shaft and hollow shaft. So power P equal to T into omega. from this equation, you have to determine the value of torque transmitted by the solid shaft. Here the power P equal to 1 lakh and omega equal to 2 pi n by 60. Okay, power P equal to T into 2 pi n by 60. Angular velocity omega equal to 2 pi n by 60. N is the speed of the shaft. N equal to 160 rpm. Now you have to substitute the value of N and P value in this equation. Now you can get the value of torque transmitted by the solid shaft. Okay, T equal to 60 into P by 2 pi N equal to 60 into 100 in here. P equal to 100 into 10 power 3. Okay, so from this equation, the torque transmitted by the solid shaft equal to 5968.3 Newton meter. Okay, now here the power is in Newton meter per second. So the value of torque also in Newton meter. Okay, now you have to convert this meter into millimeters. 1 meter equal to 1000 mm. So the torque transmitted by this solid shaft equal to 5968.3 into 10 power 3 Newton mm. From this equation, from this value, you can get the value of diameter of the shaft. Okay, already we know that from torsional equation, the torque for solid shaft T equal to pi d cube by 16 into tau. Okay, from torsional equation, torque transmitted by the solid shaft equal to torque T equal to pi d cube by 16 into tau. Capital D is the outer diameter of the shaft. Tau is the shear stress induced in the shaft material. So you have to substitute the value of T, torque and shear stress in this equation. You can get the value of diameter. Okay, from this equation, the required outer diameter of the solid shaft D equal to 75.72 mm. Okay, this is the answer for this solid shaft problem. Okay, now you have to apply same procedure for hollow shaft. Okay, given data are same. Okay, for solid shaft and hollow shaft, but for hollow shaft you have to consider diameters ratio. You have to consider K equal to inner diameter by outer diameter. Inner diameter small d, outer diameter is capital D. So small d by capital D equal to 3 by 4 equal to 0.75. Okay, remaining values are same. So the torque also same for a solid shaft and hollow shaft. Okay, in both cases the torque is same. Power P equal to T into omega is the same for solid and hollow shaft. After getting the value of torque, you have to use a torsional equation for hollow shaft. From torsional equation for hollow shaft, you have to use this formula for a hollow shaft. Torque equal to pi d cube by 16 tau into 1 minus K power 4. Okay, this is the formula for hollow shaft. Okay, this formula is the only difference between solid and hollow shaft. Remaining values are same. Okay, now you have to substitute the value of torque and shear stress in this equation. You can get the value of outer diameter of the hollow shaft. Outer diameter capital D equal to 85.96 mm. Okay, now you have to substitute this outer diameter value in diameters ratio. Okay, you have to substitute this capital D value in this equation. Capital K equal to small d by capital D. Okay, from this equation capital D, so you have to substitute value of D. Now then after you can get the value of inner diameter. Okay, inner diameter equal to capital K into capital D. Okay, from this equation inner diameter small d equal to capital K into capital D. So 64.47 mm is the required inner diameter of the hollow shaft. Okay, this is the answer for this hollow shaft. Okay, there is only one difference between a solid shaft and a hollow shaft. There is torque for solid shaft and hollow shaft. Okay, only this one and this one is the difference between solid and hollow shaft. Okay. Now coming to the another example problem. A shaft is transmitting 100 kilowatts at 160 rpm. Find a suitable diameter of the shaft if the maximum torque transmitted exceeds the mean by 25%. Take maximum allowable shear stress as 70 megapascal. Okay, Now this is the another question for a halo shaft. A halo shaft is transmitting 100 kilowatts at 160 rpm. Find a suitable diameter for this shaft. If the maximum torque transmitted exceeds the mean by 25%, take maximum allowable shear stress as 70 megapascal and the diameter ratio as 3:4. Okay, the question is same for solid and a halo shaft, but for a halo shaft, you have to consider diameter ratio. Okay, these are the given values. Speed of the solid shaft n equal 160 rpm, tau equal to 70 megapascal, and yeah, power P equal to 100 kilowatts. So same as the previous problem, but here you have to consider maximum torque. Okay, here the maximum torque is 25% greater than the mean torque. Okay, that means you have to consider 25% extra torque. Okay, so 100% is the initial torque. After that, you have to consider extra 25% torque. Okay, the total torque is 125% T main. 125% divided by 100 equal to 1.25. 1.25 into T main. Okay, T main equal to T. So maximum torque equal to 1.25 into T. Power transmitted by the shaft. Already we know the formula for power transmitted by the solid and halo shaft. Okay, from this equation, the torque transmitted by the shaft, torque T equal to 60 into P by 2 pi n. Okay, P equal to 100 into 10 power 3 watts. So, and 2 pi n equal to 160 rpm. Okay, from this equation, the torque transmitted by the solid shaft T equal to 5968.3 Newton meter. 1 meter equal to 1000 mm. So 5968.3 into 10 power 3 Newton mm. Okay, this is the torque transmitted by the solid shaft. After getting the value of torque, you have to determine the value of maximum torque. Maximum torque. You have to substitute this torque value in this equation. You can get the value of maximum torque. Okay, maximum torque equal to 1.25 times the mean torque. Okay, so from this equation, T max equal to 74,60,375 Newton mm. Okay, after getting the maximum torque, you have to use torque for solid shaft formula. From torsional equation, torque for solid shaft equal to T equal to pi d cube by 16 to tau. Okay, so here the T is the maximum torque. You have to substitute the value of maximum torque in this equation. Now from this equation, you can get the value of outer diameter of the solid shaft, D equal to 81.57 mm. This is the required outer diameter for solid shaft. Okay, now repeat same procedure for a halo shaft. Okay, given values are same up to here, up to maximum torque. The answer is the same as solid shaft. Okay, given values here, the diameter ratio is 3:4. Okay, so K equal to D by inner diameter by outer diameter equal to 0.75. Okay, this is the only difference between solid and halo shaft. For halo shaft, you have to consider diameter ratio. Okay, that is the only difference between both cases. Up to maximum torque, the given data is same. Answer is same up to maximum torque. Okay, so here you can observe up to maximum torque, the answer is same. Okay, for halo shafts, you have to consider this formula. Okay, for a halo shaft, the maximum torque equal to pi d cube by 16 to tau into 1 minus k power 4. Only this one is the difference between solid and a halo shaft. Okay, now you have to substitute the value of K equal to 0.75. Okay, after substituting the value of torque, maximum torque and shear stress and K value, you can get the value of outer diameter of the halo shaft. Okay, outer diameter of the halo shaft to capital D equal to 92.60 mm. After that, you have to substitute this outer diameter in this equation. you can get the value of inner diameter. Inner diameter equal to small d equal to diameter's ratio into outer diameter equal 69.45 mm. Okay, this is the final answer for this problem. Now coming to the another example. This problem is very important on the for exam point of view. Okay, this is the question for Halo shaft. A shaft is transmitting 100 kilowatts at 160 rpm. Find a suitable diameter of the shaft. If the maximum torque transmitted exceeds the mean by 25%, take maximum allowable shear stress as 70 megapascal. The shaft is not to twist more than 1.5 degrees in a length of 3 meters. Take C equal to 80 gigapascal. Okay. Here the angle of twist is 1.5 degrees and the length of the shaft is given. So you have to design a shaft on the base of strength, and also you have to design a shaft on the base of stiffness and rigidity. Okay, the question is same for a hollow shaft, but you have to consider a diameter ratio. Okay. The given values are speed n equal to 160 rpm and shear stress, maximum shear stress tau equal to 70 megapascal. 1 megapascal equal to 1 Newton per mm square. And this is the power transmitted by the shaft, power P equal to 100 kilowatts. Okay, same as previous problems. Okay, yeah, the torque T equal to 5968.3 into 10 power 3 Newton mm. Here the maximum torque is given. Okay, here the maximum torque is 25% more than T mean. So you have to consider maximum torque equal to 1.25 mean torque. Okay, same as the previous problem. Okay, maximum torque equal to 1.25 into T. T equal to T max equal to 74 lakhs 60,375 Newton mm. After getting the maximum torque, you have to determine the suitable diameter of the shaft on the basis of strength and on the basis of stiffness and rigidity. Okay, in first case you have to consider a strength of the shaft. Already you know that from torsional equation, the torque for solid shaft T max equal to pi d cube by 16 into tau. You have to substitute the value of maximum torque and shear stress in this equation. You can get the value of outer diameter of the solid shaft. Okay, so T max equal to 74 lakhs 60,375 and tau equals 70 megapascal. Okay, now capital D is the outer diameter of the solid shaft. The required outer diameter of the solid shaft equal to 81.57 mm. Okay, this is the diameter of the shaft on the basis of strength. Okay, but here the angle of twist 1.5 degrees and length of the shaft and shear modulus is given. So from these three values, you have to determine the required shaft size. Okay, so you have to calculate the diameter of the shaft on the basis of rigidity and stiffness. Okay, so here theta equal to 1.5 degrees, that is the angle of twist. You have to convert this angle degrees into radians. 1 degree equal to pi by 180 radians. So you have to multiply 1.5 degrees with pi by 180 degrees. Okay, here 0.0262 radians. Okay, we must convert degrees into radians. Now length of the shaft L equal to 3 meters. So this is the torsional equation. Okay, from torsional equation tau by r equal to T by J equal to C into theta by L. Okay, you have to determine a suitable diameter of the shaft. Okay, so here T is the maximum torque T max and J is the polar moment of inertia, C is the shear modulus, theta is the angle of twist and L is the length of the shaft. Okay, here T max equal to 74 lakhs 60,375 divided by pi d power 4 by 32 for solid shaft. This is the formula for polar moment of inertia of a solid shaft. Okay, equal to C equal to 80 gigapascal. 1 gigapascal equal to 10 power 3 Newton per mm square. Okay, and this is the value of theta. This is the value of C, shear modulus. And here L equal to length of the shaft, L equal to 3 meters. 1 meter equal to 1000 mm. So 3000 mm is the length of the shaft. From this equation, the diameter of the shaft D equal to 102.12 mm. Okay, this is the required diameter of the solid shaft on the basis of stiffness or rigidity. Okay, taking larger of the two values, from these two values, the larger value is 102.12 mm. So the required suggested diameter of the shaft is 102.12 mm. Okay, this is the final required diameter of this solid shaft. Okay, this is the question for hollow shaft. The question is same for solid and hollow shaft, but for a hollow shaft you have to consider a diameter ratio. Okay, so here up to maximum torque, the given values are same. Okay, so there is no difference between solid and a hollow shaft up to maximum torque. Okay, now in case 1, you have to consider T max equal to pi d cube by 16 into tau into 1 minus k power 4 for hollow shaft. Okay, this is the only difference between solid and hollow shaft formulas. Okay, now here k equal to 0.75. Okay, and tau equal to 70. Okay, T max equal to same as the solid shaft. So you have to substitute these values in this equation. You can get the value of outer diameter of the solid shaft. Okay, here outer diameter capital D equal to 92.660 mm and inner diameter equal to k into d. K is the diameter ratio. 69.45 mm is the inner diameter of this hollow shaft. Okay, so these are the shaft diameters on the basis of strength. Okay, now you have to design a shaft on the basis of strength and rigidity. You have to use the same formula for hollow shaft. Okay, but here the value of J is different for solid and hollow shaft. Remaining values are same. Okay, here this is the formula for hollow shaft. Pi d power 4 by 32 into 1 minus k power 4. Okay, this is the formula for hollow shaft. Okay, polar moment of inertia for a hollow shaft. Remaining values are same. Okay, from this equation you can get the value of inner and outer diameters. Capital D is the outer diameter, small d is the inner diameter. Okay, this is the answer for hollow shaft. Okay, from these two problems you have to observe the main difference between hollow and solid shafts. Okay, here in solid shaft you can observe, so this is the formula for solid shaft, this is the formula for hollow shaft, and here so pi d power 4 by 32 is the formula for polar moment of inertia for solid shaft. Here pi d power 4 by 32 into 1 minus k power 4 is the formula for polar moment of inertia of a hollow shaft. Okay, only these two formulas are different for solid and hollow shaft. Okay, remaining procedure is same. In next class I will explain about remaining problems. Okay.